Welcome back to AP Physics. Last time we talked about Biot-Savart law and deriving down magnetic fields. This time we're going to go into Ampere's law, which takes advantage of highly symmetrical situations. And I want to parallel it back to Gauss's law. I'm going to conserve space a little bit and right here inside of our circuit. Gauss's law for electric fields, closed integral of E dot dA equals Q enclosed over epsilon naught. When we came up with that, we started with the idea of electric flux, E dot A, integral of E dot dA, and then we did some algebra to be able to come up with an expression on the other side, Q enclosed over epsilon naught, which is a fairly easy expression, and we put those together to be Gauss's law. Ampere's law, we're going to start with the same idea. So if we look at the simple circuit I have drawn on the right side, you've got just a wire, and that wire results in a magnetic field because of the current going through it. And so over on the left side, you've got an end view of the wire, and that current is coming out of the screen at you. So if you point your thumb in that out of the screen at you direction, your fingers will wrap counterclockwise. And so this magnetic field here will circulate around in that counterclockwise direction. So if we consider not flux, but the same idea kind of as what we did with Gauss's law, the field went through an area. So we did E dot dA. Over here, this field is along a line. And so let's consider the integral of B dot ds. I could imagine a ds chunk to be just a little bit of this line. So if we consider the integral of B dot ds, well, at this location R, we have an equation to calculate what that B is. So then integral from our Biot-Savart law, we know this is a mu naught I over 2 pi, in this case R, that's dotted into ds. Well, the dot product is the direction between B and ds. So if I draw the direction of B right there, B is going to be in the same direction. Purpose of a dot product, cosine theta, is to put those two in the same direction. They're already in the same direction. So then this is going to be the integral of mu naught I over 2 pi r ds. Well, let's think about what's constant. Mu naught I, 2 pi and r, it all pulls out. So I've got mu naught I over 2r integral of ds. Well, integral of ds is going to give us the length of that loop, and the length of that loop is going to be the circumference, which is a 2 pi r. So mu naught I over 2 pi r multiplied by the length of s, which is 2 pi r. Obviously our 2 pi r's divide out, and we're left with the expression mu naught times I. And so then Ampere's law, integral of B dot ds is equal to mu naught times I. Now, adding a couple things to this. In order to apply, we have to be able to deal with that entire field at that location, which means we have to be able to deal with that entire loop. So then I'm going to add the closed symbol on our integration, recognizing that is a closed loop. It's not an area this time because we're not integrating with respect to dA. It's a loop because we're integrating with respect to ds. Now, that current that we used is the current that is inside the loop. So this is our Ampere's law equation. The integral that we have here is a line integral. So the same way with Gauss's law, we made the calculus easy by sidestepping it and doing geometry. Same thing's going to apply here. we're going to sidestep the calculus, and the geometry we're going to do is going to be that line integral, which might be a circumference or the length of whatever Amperian loop. An Amperian loop is basically just a closed loop, which is the counterpart of a Gaussian surface. So this equation only applies when you have a closed loop. And again, the other thing I want to emphasize is that is the current that is enclosed or inside of that closed loop. Now let's consider a derivation. Long straight wire, radius r, carries a steady current I, uniformly distributed across the cross-sectional area. We want to calculate the magnetic field at a distance r from the center of the wire, such that we are basically outside the wire and inside the wire. Outside the wire, reasonably straightforward. Inside the wire, a little bit more fun. So if we consider part A, I'm going to draw my wire on end view. So I have a current that is coming out at you. Then the magnetic field is going to circulate around. I'm just going to draw one loop there. Step one, we start with the equation. Ampere's law, closed integral of B dot ds equals mu naught times I inside. Second step, specify our different quantities. So I'm going to draw a little ds right there on our loop. At that location, we also know that B is in this direction, and also specifying R. So then our Amperian loop goal here, make the dot product easy. So you want B either parallel to ds or perpendicular to ds at all locations. So our logical choice here for an Amperian loop would be a circle. So that is our Amperian loop. At every location on that Amperian loop, B has a constant value. So B is going to pull out of our integral. The dot product is going to have a value of 0 degrees. Cosine of 0 is 1. So then I'm going to end up with B closed integral of ds. So all this is equal to mu naught I inside. Closed integral of ds is just going to be the circumference, and the circumference is going to be a 2 pi r, and that's equal to mu naught times I inside. Solving down for B, B is equal to mu naught. The I inside is all the current, so that's just the I value over 2 pi r. And that's the equation we've previously derived down for a long straight wire when you are outside the wire. Part B, I'm going to draw the diagram again. I'm going to draw our wire a little bit larger this time so that we have the ability to diagram inside. So there's our wire with our current. Magnetic field, still going to be in the same direction. So I'm going to draw a counterclockwise magnetic field. So then step one, equation. So now if I draw my variables, I'm out at a location R. Here's my ds chunk. And I know at the location, it's in the same direction as B. And so we're going to get constant value B, dot product equals 1, B closed integral of ds equals mu naught I inside. Closed integral of ds is going to give us just an S, which is going to give us just the circumference, 2 pi r. Mu naught I inside. And we solve down, and we get B is equal to mu naught I inside over 2 pi r. Now, it may look like we're done, but we're not, because now we have to deal with I inside. And so if we consider I inside, it's not going to be the entire current, because there's some current in the wire outside of our given location. So then we're going to need to do some math substitutions. Well, that current is uniformly distributed throughout the cross section of the wire. That basically means we're going to set up a proportion, and we're using the idea of current density, I over A. So then I over A when you are inside the wire is equal to I over A for the whole wire. So then setting up that proportion, I inside over the area inside, which would be pi little r squared. Got to go back to our diagram for a second here. Capital R is right there. So then the entire I, the area would be a pi over capital R squared. So when we solve down for that I inside, then we're going to get the expression of little r squared over big R squared multiplied by I. So it's a proportional to the ratio of the squares of the radius. Bringing that result back over here to the side, I'm going to get B is equal to mu naught over 2 pi little r times little r squared over big R squared times I. One of our little r's are going to divide out, and I'm going to get a mu naught I over 2 pi capital R squared. And then I have this little r hanging out here. This is our equation for the field inside a wire. So I kind of separated out the little r because I want to emphasize everything else in that equation is a constant. So then inside the wire, you're linearly proportional to r. Outside the wire, up above, you are inversely proportional to r. So then if I squeeze in down here a graph of field versus distance, whereby right there is capital R, then inside the wire, that would be linear to r. Outside the wire, you're proportional to a 1 over r, so over here you're proportional to an r, and that's what our graph of our field looks like. Now we want to apply this to two different geometries, essentially. Here's a toroid. A toroid is a circuit element. Basically, it's a coil of wires bent into the shape of a donut, and with that shape, what you produce is a magnetic field of a known value inside the toroid. By inside, I mean inside the coils themselves. So if that's a donut, you're not in the donut hole. You're inside the actual breaded part of a donut. So that's what a toroid is. In a solenoid in a minute, okay, on the simplest sense, they are devices that will produce a known magnetic field. I want to focus more on a solenoid than a toroid, so I'm going to, in passing, talk about a toroid. Here is the equation for a toroid, and basically summarizing a little bit through Ampere's law, closed integral of B dot ds equals mu naught I inside. The Amperian loop that we've drawn is inside the donut part itself, and that is the dashed blue line, and that is parallel to the magnetic field. For that toroid, you can wrap your fingers in the direction of the current, which would go into the inside of the toroid, and your thumb will point the direction of the magnetic field. And so then basically going through Ampere's law and the substitutions with I inside right here, when you get down to that point, you just have to do a simple substitution with a multiplier. How many wraps you have, because each time you have a wrap go through, which would be on the inside of the toroid shape, then you accumulate another current. So you've got 1, 2, 3, 4, etc. You've got a bunch of different currents, so you just need a multiplier on there. Now, coming to the idea of a solenoid is basically a coil that's straight, and you're going to find solenoids that are used more often in things than you have toroids. So I do want to take some time to be able to go through the derivation for this one. You have the diagram of the field. Looking at the current direction here, on the right side, it's going up that first loop. So on all of these, on the front side, it's going up the front loop. So if you have your hand with your fingers going up the front side, wrapping around to the backside, your thumb is going to point to the left. And so that's where the blue lines come from. You can do the other right hand rules also, but there's kind of a shortcut one, just wrapping your fingers in the direction of the current in the solenoid, and your thumb points the direction of the magnetic field. Notice on the magnetic field, most of the magnetic field is inside, and outside it is very limited. You have a very weak magnetic field outside. So then outside, we will oftentimes approximate that magnetic field to be 0, and we'll call that the ideal situation where all the field is inside. In a larger sense, if you have ever had an MRI, then that tube that they put you inside of is a solenoid. So in an MRI, you're placed in a very strong magnetic field of known value, and it's of known value because you're inside of a solenoid. Now let's derive an equation down for the magnetic field inside of a solenoid here. Over here on the right side, just below the field diagram, I've kind of drawn the coil sliced in half so that we can diagram a little bit more. I'm going to draw a little bit of the field. And so there are a couple of magnetic field lines there. Not drawing a whole lot because I want to leave room for other stuff. Step 1, write the equation. Second step, we need an Amperian loop. This Amperian loop, remember the dot product. We want the loop to be easy so that every side of the loop is either parallel or perpendicular to the magnetic field, and it has to have current inside that loop. So I'm going to draw my loop such that I have a line here, then I work my way across, and then I come up, and then I work my way across. So then that's basically a rectangular Amperian loop, numbering our sides. So then to evaluate this, we have to evaluate for sides 1, 2, 3, and 4. On side 1, you've got a ds chunk. So there is my ds chunk, but it's going to be perpendicular to the field. Perpendicular to the field, the dot product is going to give us a 0. So on side 1, we've got 0. On side 2, I've got a ds chunk right there. I'm going to have a value there because I'm going to be at 180 degrees, so I'm going to get a cosine of -1. The negative we're not terribly concerned with. That's a directional thing. So on side 2, I am going to get a value. That's going to be a b times the length of the side, s. Side 3, similar to side 1, you're at a 90-degree angle, that's 0. Side 4, you're outside the solenoid, and outside the solenoid, the field is approximately 0, which means b dot ds, you've got nothing to dot into ds, so that's going to be a 0 also. So then when the dust settles, all I have is b times s. I'm going to specify here a length of the solenoid. So I'm going to change that variable to an L, and that's going to equal mu naught I inside. Solving down, this is mu naught I inside over L. Now we have to deal with I inside. Same idea as before with toroid. You have a bunch of different currents that you are intercepting. So you are intercepting a lot of currents, so then we can throw in the multiplier, capital N, multiplied by what the current is in a singular wire. So then we're going to get B is equal to mu naught, capital N times I over L. Now, I'm going to take this one more step. Solenoids are typically rated in how many turns they have per centimeter or per meter. So little n is the total number of turns over the total length. So then we can put that in there, and we get mu naught small n times I, and that is the equation for the magnetic field of a solenoid. Remember, small n is just total turns over total length.